Awesome. All right, so hello everyone. My name is Lotzi Thompson, and I would like to introduce you to Group 3, otherwise known as Stellar Sunshine. This team is comprised of Cam, Thierry, Armand, Elijah, Cameron, myself, and Wenja. We are going to walk through what makes us unique as a team during this presentation. And we're going to dive into our overall product and kind of really get into the nitty gritty details of each subsystem that we define and how the things that we designed meet the customer needs. And I'm going to let Wenja kind of get things rolling there.
I am Wenja, and for our team, we focused on the structure and actuation design. That's a combination of our group's passion, strengths, and economic purpose. And now I will introduce our product and talk about each subsystem and how they're connected. Start from the bottom. The first subsystem is the structure system. We use the pressure-treated pine wood driving into the ground. On the top of that, an oil-light thrust bearing connected the pine wood and the PVC frame. The bearing is from Maneuverability Subsystem, which enable our module to rotate. On the pine wood, an Arduino from tracking system is attached to it. The PVC and steel frame are connected and used to support the heliostat. The solar mirror film from reflective subsystem adhere to the steel frame. And that's the overview of our product. The detail of each subsystem will be introduced in the following slide.
Hi, my name is Thierry Montplaisir. Going over the reflective subsystem overview, we can see a tool description where we have 4 square mirrors and the 20 gauge galvanized steel backing plate as illustrated in each view. Here, the reflective customer needs map is used to verify that we address each metric. We'll dive more into details about the customer needs and the metric for the reflective subsystem. Need 2 clearly states that the area of a single heliostat module must be less than or equal to 1 meter squared. The area was made by simply calculating the area of each mirror. Then it was multiplied by the number of mirrors of the heliostat. Ultimately, the reflective area of a heliostat is 0.81 meters squared, which is under 1 meter squared. Thus, the customer need number 2 is met. With customer need number 3, each module must be composed of 4 to 16 heliostat. This picture illustrated on this slide shows that we meet the customer needs with our 4 mirrors.
Now I'll continue to introduce the need number 6. In order to let each heliostat unit not shading on each other, we calculated the ratio of the shading area over the reflective surfaces. A geometric method along with the values of angles and distance are used for calculations. The specific calculation steps is listed in the PowerPoint. We designed the frame and mirror size to lower this value as much as possible. We reach an average shading ratio of 6.79% during a regular day. The main reason that we decided not to make this design to reaching a 0 shading is because the benefits of 0 shading offsets the cost of a material. The solution to the shading problem is to have this 4 heliostats listed in one line, and this results in a longer rod and longer frame. It not only increases the material cost of PVC, rod, and metal, but also cost of motor, since we can't use the geometric benefits of the structure or have the motor in the center anymore. And what's more, the tracking arrow could also be increased since the bending stress will increase in that design. And for need number 12, our design is also washable. A yield strength of 2,750 psi is required for a part to be washable. well, the heliostats are made of solar frame. It has a yield strength of 7,935, which is qualified for this requirement. And the recommended way of washing is pressure wash.
So as Wenju just mentioned, our material for the reflective concept is a solar film produced by 3M. Our original design used Mylar for the reflective surface, but research showed that it would start to yellow and become flaky after about 2 months, which obviously that's not ideal. So we decided to make the change to the 3M solar film because it lasts longer. So need 15 addresses the fact that the operational life of the heliostat module is to be more than 20 years. 3M released this data sheet for the solar film in 2012, and it had ongoing data from 1995. That's where this graph is from. And you can see that its reflectivity is very high throughout that 17-year study that is continuing to go. And so therefore, because it only dropped by less than 3%, you can conclude that it will in fact last the duration of the 20 years required in the user need. More on the material specific metrics that we met. We defined metric 19 as having a reflectivity of at least 90%, and the solar film that we are using has a reflectance of 94, as seen in that previous slide. So this user need specifies that 1 megawatt is to be produced. So for this user need, we determined that the number of heliostats required were determined from that 1 megawatt. So you can see in our math, we account for that and some loss in order to determine the number of heliostats required. And then therefore we have to meet that metric. Similarly, user 18 says the solar concentration ratio must be greater than 1,000 suns. So we define this as having an average delivered flux of 174,300. And you can see that in the orange box there, how we got to that number. So a heat transfer analysis was conducted here to determine the delivered flux as a function of the flux delivered to the earth from the sun and as a function of the reflectivity of the material. So when you account for the total number of heliostats, it's clear that the delivered flux is over 1 million, which is far exceeding the 174,000 that we defined in the user needs.
I'm Cameron Mahorn, and I'll be going over the customer needs map for the structure subsystem. So as you can see in the map, those are the needs that need to be satisfied by the structure subsystem. And we'll go over that in more depth later. So the structure subsystem can be broken into 2 parts. There's the PVC frame that supports the reflective surface and a long wooden pole that's going to be driven into the ground. So in the picture you see to the right, it's around 6.5, the vertical wooden post around 6.5 feet tall, but that'll be mostly driven into the ground to support the modules. So to determine the overall height of the heliostats, we added together the height of the PVC support and the wooden, the vertical wooden support after it was driven into the ground, and that came up to a total of 0.6 meters, which met customer need 1. And then to find the, so for customer need 10, the module's reflective area relative to the reflecting area should be small. We interpreted this as the structure that was impeding the reflective area had to be relatively small. So we looked for a ratio of over 85% reflective area to structure. We came to a conclusion that our ratio was around 0.92, which satisfied that customer need.
Hello, my name is Armand Pasqua, and I'll be wrapping up the structure analysis. So for need 13, the factor of safety must exceed n equals 2. So what we did was we found the force of the wind against one of the mirrors, multiplied that by 4, and then added the force of the gravity onto the structure to find the total force on the whole subsystem. Using that, I did a buckling analysis on the wooden post itself and found a factor of safety of 1,910. This is a bending analysis on the PVC with the forces going in this direction. I was able to find a factor of safety of 2.94, assuming that the four PVC supports supported or distributed the mass equally. Need 15 stated that the operational lifetime of the installation must exceed 20 years. So for wood, since it's a brittle material, the wood is not going to fail structurally unless the maximum stress exceeded the ultimate stress of the material, which did not occur. However, since the PVC can be considered a ductile material, we found the fatigue strength of the PVC under the cyclic loading of wind throughout the 20 years. We estimated that the strong gusts that we found occurred 10 to the 5 times throughout those 20 years, and therefore determined a fatigue strength of 33.93 megapascals, which was much greater than the maximum stress that the PVC ever experienced with forces in this direction. Therefore, the lifespan would last longer than the 20 years. For need 16, we determined that the structure must last within the Las Vegas conditions. This had two components. One, the temperature of Las Vegas couldn't harm the PVC mechanical properties in any way. We found that the maximum temperature throughout the day was 47.8 degrees Celsius, and PVC starts to experience material property distortion around 60 degrees Celsius. So there was no issue with temperature. The next issue was that we had to determine that the PVC and wood would be safe with the wind coming from the side. So if you go to the next slide. This is a bending analysis we did on the PVC with the wind coming from the side, acting on all four heliostats, and we found that the factor of safety was 8.7. And this is a bending analysis we did on the PVC with the wind acting in this direction and found a factor of safety of 5.524.
All right, so I'm Elijah Rice, and I'll be talking about the maneuverability subsystem. So we designed our subsystem around the customer needs 5, 7, 14, and 15, which related to the heliostat's ability to track the sun, which was comprised of its rotational freedom through elevation angles and azimuth angles, ability to reflect to the target, independent movement of axes, and then also, of course, designing around a lifespan of 20 years. So for our maneuverability subsystem, we chose to use 2 DC motors. And the reason for this is that motors comprised a pretty large share of the cost. So reducing the number of motors we use in our design was helpful in trying to limit the cost of our modules. So for azimuth rotation, we used 1 DC motor that operated very similarly to a Lazy Susan. It rotates the mounting plate, which sits on top of an oil-light thrust bearing. And this thrust bearing helps to reduce the wear on the motor due to axial loading. And it also reduces the contact friction from the mounting plate for the upper frame's rotation. And so this oil-light thrust bearing works by releasing a lubricating oil that is centered into the material when friction is present, which is excellent for our intended use, which is there's going to be contact friction at very slow speeds while the heliostat tracks the sun. And then for our altitude rotation, we wanted to actuate each motor independently, but also reduce our motor costs by driving rotation with a single motor due to the relatively high cost of DC motors. Our customer interview indicated that that driving the altitude rotation with one motor through a chain and sprocket drive counted towards that independent actuation. So we found that this was the cheapest method to do so. And then we also incorporated some tensioning rods around the sprockets that can be moved up or down within cut slots on that middle bar. And the reason for that is to increase the number of teeth on each sprocket that are interfacing with the chain, and also to just generally increase the tension on the chain drive so that we don't have issues with backlash that'll cause our mirrors themselves to lose accuracy aiming towards the receiver. So here is a quick animation of the actual rotation of our module. So as you can see, the azimuth rotation, that base plate rotates 360 degrees freely. And then also for our elevation rotation, you can see that each mirror is able to simultaneously rotate 360 degrees as well, with clearance on every side. So just verifying the customer need is met. Again, you can see that rotation 360 degrees is possible in both axes. So because of the freedom in rotation in both axes, our module is able to redirect sunlight to the receiver target mounted on top of a 100-meter tall tower at any field position. So whether that be 10 meters away from the base of the tower, 100 meters away, because it's able to rotate through all those angles, it can redirect sunlight properly. And then 14, like I was talking about earlier, each mirror needs to be independently actuated. And so the way that we accomplished that was with pseudo-independent actuation via the chain and sprocket drive, which drives the elevation rotation of each mirror. And then for need 15 for the operational lifetime of installation. So the way that we calculated this was figuring out how many cycles a motor went through in a day, and then how many cycles the motor would last until failure. So it was cited as lasting 180,000 cycles on average, and assuming one cycle each day, since you only need to rotate 90 degrees in the elevation direction and 180 degrees in the azimuth direction, and then rotate back at the end of each day. We just went ahead and assumed one cycle for each day, which for that calculation gave us an operational lifetime that far exceeded the 20 years that we were required to last. And then we chose to base this off of our motors simply because the motors are the most likely component within the maneuverability subsystem to fail if a component does fail.
So I'm Cameron Sirajadini, and the tracking subsystem will work to ensure that the modules in the field are in constant sync with the sun as the Earth moves relative to the sun. Therefore, it must have a low tracking error to stay with the sun and collect the most solar energy, in addition to being able to withstand the environmental conditions of Las Vegas and last at least 20 years in Las Vegas. The tracking subsystem is contained in a box composed of 1023 carbon steel sheet metal, with a slot below for the wiring to make its way to the motors and vents on the side to ensure that the temperature reached inside the box on a hot day in Las Vegas will not exceed the maximum operational temperature of the Arduino and motor drivers. The fact that the motors precision will not result in optical losses greater than 40% was proven based on the counts per revolution value and reduction ratio given in the motor specifications. The accuracy in degrees per count is roughly an order of magnitude smaller than the maximum uncertainty in the motors. Each module will be able to have a single tracking subsystem bolted onto the wooden post, which will be close to the ground after the post is driven into the ground and covered mostly by the mirrors, ensuring that it will remain out of the sun as much as possible. The life of the tracking subsystem exceeding 20 years was proven with the specifications of the motor drivers and from the rule of thumb lifetime for electrolytic capacitors, which are inside the Arduino. And because of the hot temperatures induced in Las Vegas for long periods of time, an energy transfer balance was done on the electrical enclosure box. It was determined that free convection from the air, from the surrounding air, and possible radiation from the sun itself were the types of heat transfer that would possibly harm the inside components. The viewing factor for radiation was proven to be very small, therefore proving that radiation did not play a part in the heat transfer. Therefore, the free convection was the only component that played a part in heat transfer, and it resulted in a maximum temperature inside the box for worst case scenario, still less than the operational temperature.
Right. So talking about what makes our design unique. So for our reflective system, our solar film from 3M has not really seen much commercial use. And because of its long lifetime and high specular reflectance, it really allows our design to reflect high volumes of sunlight. For the maneuverability, our sprocket and chain drive, which reduces the cost and the ease of fixing tracking error. For the maneuverability subsystem, is also something that's unique to our design. And then for our structure, the use of the oilite bearing is really great since it reduces the cost of having to have something like a sealed ball bearing, thrust bearing. Since we're operating in these low speeds, having just a solid ring washer that acts as the thrust bearing is a lot easier to not only assemble and manufacture, but also to maintain, since sand is obviously an issue in the Las Vegas desert.
Cam, you're muted.
Sorry about that. Here we have the cost summary per module. To find the cost per module, we added the off-the-shelf parts with the raw materials, and then use a Boothroyd-Dewhurst insertion and handling table to come up with the manufacturing and assembly cost. Our total came up to $281.64, which is over the $100 specification, but it should be noted that our materials and systems don't need any tune-ups. They don't really need any human intervention once they're installed. So the long-term cost will be lower than other designs you may see. Yeah.
So to sum up everything we've talked about, our heliostat is really great at tracking the sun since it can rotate all its mirrors in 360 directions in both the azimuth and the altitude axes. The square pattern helps to mitigate some of the self-shading, and we have a really great reduction ratio that allows high accuracy when the motors and the tracking system are working together to track the sun. Furthermore, all of our materials are extremely long lasting and are unlikely to fail. And we estimate that there is no part replacement needed within the 20-year lifetime. Why we should be chosen as a prototyping, why our design should be chosen to prototype an EML4502. We found that everything that we don't buy off the shelf that we machine is relatively easy to make. The sheet metal has extremely simple geometry, and The two motors are cost effective with high accuracy. Also the installation process is extremely cheap with just having to drive the wooden post into the ground. That is it for our presentation. Thank you so much for attending and listening to us. This is Group 3, Stellar Sunshine. And now we'd like to open it up to any questions.
Hey guys, this is Tom Singer from Northrop Grumman. I've got a few, and I know we have like hours until the next presentation starts. So I'll ask a couple, and then maybe a couple other folks can jump in, and then maybe I'll come back at the end and you know, take as much time as you're willing to spend on this. The first thing I noticed was it looked like your wood post was cylindrical. Is that?
Yes,
Why is it cylindrical?
because you can buy it at Home Depot.
Okay. You can also buy, I mean, presumably if you're manufacturing these at scale, you're not buying them from Home Depot. I would suggest that it's a lot easier to cut square things out of wood. So I would imagine a square post might work a little bit better for you. What about in terms of life, right? I mean, you said this is pressure treated pine. It's going to be buried in the ground. Is 20 years in the ground something that is feasible for a wood structure?
I believe so. Somebody else can chime in on this question if they have more to add, but I believe when we did the research, because of the nature of Las Vegas is pretty dry, and the ground there it's not like Florida, right, where you can have a lot of moisture get into the wood and cause it to rot once it's driven into the ground. Because of the dry nature, it's more likely to last the duration of the lifetime.
Yeah. Okay. Yeah, that's something that, and granted, you know, I don't have any experience with wood structures, and I don't really have any experience with Las Vegas either. But that's something that just sort of jumps out at me as something to think about. I love that your presentation was focused on customer needs, and you had a bunch of slides where you said this is how, you know, this is the need and this is how we're meeting it. I really appreciate that. Some of the needs that I remember, because I've looked at these, you know, going back to last semester, and some of this stuff is kind of stuck in my mind. There was a customer need for independent actuation of the mirrors. How it looks like all of your mirrors are actuating as one.
Yeah, so this was something that it was a little weird because the customer needs stated independent actuation, but the customer also specified that that having like a belt and pulley or a chain and sprocket, or just some sort of like transmission from one motor across multiple axes still counted, as long as you weren't, you know, having, say, all of the mirrors stay coplanar and then rotating the frame. As long as you were rotating the mirrors themselves, that was enough to satisfy the need.
Yeah,
So
Eli, do you want to go to the other one?
Is that something that you actually like asked the customer about?
It's
like, did you have access to a customer to ask them?
Well, we didn't ask them directly, but it was in the customer needs document they sent us. They said as long as they rotate amongst unique axes. So because our design, each mirror has its own axle that it's rotating about, while it is from the same motor technically, because they're independently moving on their own axle, it qualifies as independent motion.
Okay. What about their need on tracking error? I think their tracking error was like 40%. I think, and I spent more time than I should have yesterday kind of working through like the geometry of reflecting sun to a tower. And that optical tracking accuracy of 40% thing really had me scratching my head. And I think the way that you guys were interpreting it, you met it by like orders of magnitude more than what the customer was requiring. And I wonder if maybe you thought that maybe you were interpreting that incorrectly and took an opportunity to ask the customer about that need.
Cameron, do you want to take this question?
Yeah. So basically what we determined was the motors that we're using have they just have like such a small accuracy with the number of counts per revolution that with that accuracy, with that angular accuracy, it was shown that if that was implemented, that it will result in the tracking errors less than 40% if the motor has that accuracy.
Yeah, we just determined that the accuracy was a function of, one, the ability of the tracking system to actually point in the right direction, and then also the ability of the reflective material to reflect light specularly rather than disperse it.
Okay, so what do you, like, I guess, what do you interpret that tracking error less than 40% to mean?
So essentially, if you're aiming the mirror at the center of the receiver, that however much you're off in your angle on either axis, that the area that you're reflecting to doesn't fall outside the bounds of the receiver.
So if you've got like a 1 meter wide target, that you could be off by like 40% of 1 meter?
Yes.
Okay. That's something that's confusing me, and mostly I'm getting it. Did you talk to the customer about some of these things? Because some of these things are somewhat confusing to me, and I just want to make sure that you're taking advantage of opportunities to clarify and refine requirements.
Okay.
Yeah. So I think something that is worth adding, the plus or minus 0.25% is from the customer. That was something we did not put in the quote, but in the customer need for the verbatim text that they have is each module must mitigate optical losses, like we stated, and then below that it says tracking errors of theta plus or minus 0.25 degrees is a reasonable assumption.
Yeah, that was another one that I don't know. I mean, I don't think they would say it's reasonable to assume that your structure, which you're designing, they have no idea what that is, that you're going to have a tracking error of, less than 0.25 degrees. I think that is the wrong way to interpret that. The way that makes the most sense to me to interpret that, I think, is they're going to tell you where the sun is in the sky to within like plus or minus 0.25 degrees.
Right.
But again, I think there's a lot of room for interpretation on that, and I would suggest that it's a good idea to reach out to the customer when they have requirements that are maybe unclear or that appear to conflict, to understand exactly what they're trying to get at. And a lot of times, they'll write down a requirement that, they have an idea what they want in their head, and that gets translated incorrectly on a paper, or they'll write down requirements that they don't actually require. So all this just to encourage you to have that dialogue with your customer and understand what it is they're trying to do and how you can help them do that.
For sure. I agree.
Okay, so
All right.
we were sort of the translator there in between the customer and the students, and the plus or minus a quarter degree or half a degree error was sort of the way they originally had this one tracking metric, and then they said, well, depending on where it is in the field, and I'll just get it to within a half a degree. So the customer wants these heliostats to respond within half a degree.
Okay. I did some geometry, and I think that is a huge amount of error relative to your the one meter target, but that's kind of a separate thing. But anyway, I'll kind of step back and let other people chime in. I've got some other stuff that we can maybe revisit if people have time.
Yeah, for sure. Thank you for your questions, by the way.
Thank you. Yeah.
I'll go ahead and jump in if, ooh, let me get my camera on so you can see me. There we go. Can you go to the cost slide?
Sure.
So correct me if I'm wrong, the customer need was $100?
Yes.
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 So
I'll correct you right there. So the customer need was $100 per square meter. So don't forget, we're not even at a full square meter.
per square meter. Okay.
So the cost goes higher.
Wow. Okay. So obviously, if I'm the customer, if I'm the investor, I'm going to be like, no, that's way out of budget. So if you guys had to figure out a way to reduce costs, where are you looking at hitting this? Where would you try to reduce some of your costs?
Yeah, so we kind of talked about this a little bit as a team. I think our main thing was the galvanized steel backplating for the reflective subsystem. We were considering changing it to like injection molded ABS because that would be way cheaper. The reason we didn't do that is because then you run the risk of even more plastic in Las Vegas heat. And so, you know, that's where we're looking to make the most changes, because as far as raw material goes, I think the galvanized steel is the most expensive component.
Let me ask a question real quick. You mentioned the plastic, right? Now, if any of y'all saw my lecture, I am not an engineer by any stretch of the imagination, okay? So is plastic melting actually a concern? Because I would feel like that would have to get really hot.
It's not as much
It's not a
melting,
concern.
but
Okay.
the issue is if you're using it to back, because this film isn't rigid on its own. Think of it like an aluminum foil. It needs a frame to sit around, and the issue is under the wind loads present in Las Vegas, and under the weight of itself, you don't want, especially because those plastics lose part of their material properties, decrease in that heat. Any strain you have, so any deflection, so if you had like the square mirror, if it were to bend at all due to wind loads, or due to that loss in mechanical properties, now you have, now your light is being dispersed elsewhere rather than aiming at your intended target. So that was our major
There's
concern.
not a cheaper material than the galvanized steel to stabilize the mirror, if you will.
Yeah, we were gonna look into some more like cheaper metals.
I guess my problem is with just looking at your cost summary here, without really seeing a breakdown of what your costs are. I mean, you say 59% for off the shelves, but until we really see what they are, it's kind of hard to say, oh, you may want to look at this area, you may want to look at that area.
Yeah.
But I can tell you as an investor, as a customer, if you come to me with this, I'm not even going to consider your proposal. So definitely, let me give you a good thing though. The fact that you considered manufacturing and assembly labor, if y'all had heard me in the presentations yesterday, that people do not put that in, and I just bang my head against a wall every single time people do not put in labor costs, because that is a significant portion of your costs. So definitely thank you. Amen. Good job on that. Good job. But definitely I would say take a look, really break down what your costs are and kind of back that out and see, okay, and it's not cheaper, it's where can I get less expensive? Right. Yep.
Okay, and let me tell you, when you follow on and make 3 with this project, you will you will work with different types of plastic. So the standard print in PLA will absolutely warp in the Las Vegas heat, but we have other options, and you will get more experience with that in the summer or fall, whenever you take MEC 3.
Yeah. And then I think I was going to speak to the OTS parts as well. One of the biggest costs was actually ended up being sprockets, are pretty expensive. So costs can definitely offset as long as the failure analysis for gear teeth stress, we can check that, but changing to a printed sprocket would decrease our costs.
Yeah, so since the cost is, pretty much the biggest issue you have to address, let me ask, is this the prototype cost or the per module field cost?
This is the full production costs.
Okay.
Yeah.
And I really liked your customer needs mapping, and I really loved the way you did not type out every single word of the customer need, but you had it very well summarized in a way that someone watching your presentation would instantly understand. But one thing with your group and other groups is the cost. Like, I see this nice linear mapping of all these customer needs get mapped to one subsystem and then get mapped on out. But in your slides with the customer needs mapping, I didn't really see cost. How did you map that?
So normally we map it as we have a separate section called all subsystems, which includes lifetime and both of the cost metrics. We thought for the flow of the PowerPoint, since we wanted a cost summary slide itself, it didn't make sense to include the cost of each subsystem within the subsystem discussion, but it did make sense to talk about the lifetime of each one while we were talking about each subsystem. So that's why you didn't see the cost on the map itself, was because we wanted the map to act as an outline for what we were going to discuss.
Ah, good. I mean, I have to admit the flow went very well. It was very understandable. One way to map needs like customer cost, whether it's, money or weight or power consumption. Often it's a good idea to do a budget, like budget so much for this subsystem and so much for that subsystem, and people understand budgets.
Yeah.
Yeah.
Here's another question. Where did you guys get, like for your OTS part, where did you get those prices?
So for our OTS parts, I think the motors came off of Amazon. For all of the other components, we looked around at several different vendors that specialized in selling bulk materials. So specifically, we bought from, I think, USA Chain is like a bulk vendor of chains. So we were ordering for full production in like 500-foot rolls of ANSI number 25 chain. For our sheet metal costs, we were ordering like 4-foot by 10-foot blanks to be cut from. I'll pull up the.
Well, so it sounds like for some of these things you were ordering a bigger size than what you needed. Is that correct?
Well, so it's because what we are showing is the production rate. So what it would cost per module to fill out the whole collection field. So we would buy in bulk so that it's cheaper.
Right. That's what I was trying to get at, was were you buying big and accounting for that whole 1,000-meter whatever for one unit, or were you splitting that cost out a multiple units? Because that may be one way to, if you bought a $500 piece of aluminum foil, again, remember, not an engineer, work with me here. You bought a $500 piece of aluminum foil that would cover 50 heliostats. did you split out that cost amongst the 50, or is that all here in this prototyping cost?
We
That's-
split it up amongst the 50.
Okay.
Yes.
Well, that doesn't help reduce the cost on this thing then.
Yeah.
I mean, I'm glad you did. That's the right answer. That's what you should be doing, is splitting it up. But I was hoping maybe that was an easy way. I could be like, oh, okay, here's how you reduce your costs, or at least your perceived costs.
Yeah, unfortunately
Julie
not.
is looking for a way to invest in this project.
I am,
Uh,
man. Look, me, I just got all these extra dollar bills to be thrown around, and I'm trying to invest here.
I mean, if you're trying to see the silver lining, the good thing is the long-term cost, since nothing really needs to be replaced, is
Which actually would
more
be something
similar.
to
Yeah,
reconsider.
so and that's an interesting statement, because nobody has really in all of these presentations, nobody has really said, hey, I've got a life and maybe I've got a part that could wear out and it's easy to replace.
Yeah.
But nobody's really addressed the maintenance cost of their system.
They're lying
right?
to you.
Yeah. Let's see. Before I jump back in, does anybody have anything else? Because I've got like a list of things.
Oh boy. Let me jump back in kind of with what you were talking about there with that maintenance cost.
Mhm.
Would it maybe reconsider if a part that you have right now would last 20 years? What if you replace it with a part that would last 10 years, but is maybe 1/8 of the price? Yeah, they'll have to
Yes.
replace it once during the life of the product, and you have to consider a little bit of, labor costs in there. But if you're talking 1/8 of the price,
Yeah.
it may
Yeah.
be something to consider.
We
would
did
have to-
consider some of that. Originally, we were talking about making the reflective surfaces themselves modular. So you replace it once and like throughout the span, but then you'd have to buy more material in the steel frame to make it easily replaceable, if that makes sense. So we
Mhm.
didn't see the cost benefit in doing that for that particular subsystem. We could definitely look into that for other ones though.
Yeah, we would have to perform a cost analysis to just see what the initial savings are versus the labor costs for replacing it eventually.
Cost analysis, I love that word. I'm sure you guys are like, but me as an investor, I love that word. Okay, yep, just like I said, kind of coming from an investor business standpoint, the costs are scary, but I think there's real ways that you guys could go in and really reduce those costs. And I think you guys kind of got some ideas of where to look now.
Yes,
So I'm
I
gonna,
appreciate that.
yeah, of course. Look, and it's totally okay in these meetings to say that, I don't know. That's a great idea. We didn't consider those options, You don't have to have considered every option. That's why we're here. That's why the panelists are here. So don't be afraid to be like, oh, yeah, we didn't think of that. Good job. Let me feel smart.
Yeah.
I just have like a quick question though. So wouldn't like the unique features like the long life, the long term outweigh like the short term cost like for the moment, or is that something to be
Yeah.
considered like?
It
just
might,
like
but you
that?
didn't present anything on that.
Yeah, I mean, you
Like, you
kind of
haven't done any
mentioned that it would
analysis to
last
support that.
long. Yeah.
So we just should have offered more insight on that to show the long term would just
Yes, but
benefit.
at the same time, when you're coming at me with, 3 times what I'm able to pay,
Yeah.
Yeah. We need
yeah,
to-
long term's great and I don't have to replace it and everything, but what, you have to look in the real, realistically, I just may physically not have enough money to pay
Yes.
this.
Yeah.
It's not that I can find extra money from my company or this, that, or any other thing. My boss has said, you get X number of dollars, that's it. And so that's what I come and present to you. I get X number of dollars. And yes, that usually can be changed a little bit, not 3 times the amount. So, yes, a benefit is it does last long. Like, that's great. Hallelujah. We like that. I like set it and forget it. I'm a crock pot cooker. Okay. But at the same time, I just physically don't have this money.
Yeah.
Right.
So that's just something to kind of think of. It really is a balancing act. It's not just, hey, I can offer you the highest thing here. This is super awesome. You know, it really is a balancing act amongst all customer needs. And this is why some people like Steve Jobs are millionaires and other people like me are not.
Got it.
There's actually one more thing coming to my mind for the related to the budget. Since our structure is made of wood and our module can just driving into the ground, which can save some money on like for the floor, it just need to be the mud. But for some other designs, if they are made of like PVC or other materials, they have to mount it on a concrete ground. So I don't know if that money is also being considered.
Mhm. I mean, I'm not going to go into other people's projects.
Yeah.
Yeah.
But that would just be something else to consider, you know, for
Yes.
your project in particular.
Regardless, yes, we do need to
Lower our budget.
Yeah.
shift our focus a little bit from the long term to the short term to make it feasible as a buying option for initial price.
You know, when you say
Agreed.
switch to the short term, don't view that also as short-minded.
Yeah.
You know, believe me, that the fact that, again, crock pot cooker, that you can set it and forget it, I love it. But you know, you do have to sometimes make trade-offs. I really,
Yes.
really want to go on that, you know, Disney cruise, all inclusive with every shore excursion possible. But I don't have the money for that. So I'm going to choose the 3-day Carnival cruise.
Well,
I still get
yeah.
something, but I don't get the full thing.
I mean, it's like buying a cheap
Yeah.
used car that needs a couple fixes rather than like a brand new car that you know is convenient.
I really want the Starbucks,
Yeah.
but I'll get the McDonald's.
Right.
So you still get what you want and you're not going completely over budget. So, but like I said, you guys definitely have a good solid area in which you can dig into to reduce those costs. So you're actually in a decent situation where you can figure out a way to go down. It's just now, unfortunately, you have to do it.
Yeah.
Yeah.
And I will be done with my words here.
Thank you.
Yeah, so this is Rick Miles with Northrop Grumman. Just a couple of things. Want to kind of reiterate what Tom said about the customer, right? I kind of picked up on the same thing too. When you say you interpret customer requirements, that just that leads you down a dangerous path. There's been lots of mistakes that have been made in the defense industry when people interpreted customer requirements instead of confirming with the customer what the requirement was. So just want to kind of harp on that a little bit.
Mm-hmm.
And then when you did your buckling analysis, you talked about a factor of safety like close to 2,000 or whatever. Anytime you get a factor of safety greater than 4, just say that you have ample margin. You scare the customer sometimes when you give huge margins of safety, because basically you imply that you're wasting their money because you've got too much material in order to go about doing that sort of stuff. So just be careful how you address those sort of things. And I did also appreciate, like Tom did, how you tied the customer needs to the different subsystems. That was really nice. I thought the sprocket and chain drive was a nice novel approach, but maybe you can look at using, again, from a cost perspective, using a sprocket and chain drive that's not metallic, right? As a potential way of driving down some of your cost. And then I would just be concerned with how well the wood post would hold up over time. I know Nevada's got very dry air, but again, even pressure treated wood tends to absorb moisture over time, and that can lead to problems. So you're talking about long lasting. I'd question how long those posts would hold up over time.
Mm-hmm.
Other than that, great job.
Thank you.
Thank you.
Yeah, I would also, I mean, you can dry wood, but you know, leaving it out in the desert for 20 years is going to dry it out even further. You're potentially going to have dimensional stability problems, right? Where things sort of tend to bend and warp. You know, if you look at fence posts and you see they're not perfectly straight, even though they came out of the mill perfectly straight. So those sorts of things are sort of problematic with natural materials like that. Rick mentioned your chain drive and sprockets, and we were kind of discussing off on the side. Can you flip back to the slide where you're showing that?
Yes.
Right. So what I see here is you've got 2 lengths of chain going over the same sprocket, and you're never ever gonna get that chain to line up perfectly with the teeth of your sprocket, which means you're going to be like wearing parts prematurely. Yeah, something like that I'd be concerned about. Just chains in general are, they're expensive because they're complex, right? There are a lot of manufacturing operations that go into producing a chain. Something like a belt drive might solve a lot of your problems here. You can sort of maintain your same sprocket situation. You don't have to worry really about running multiple lengths of belt over the same sprocket like you do with chain. And it should be just generally cheaper. So I think that might be a preferable option there.
Yeah, initially we had looked at the belt system, and I think if we move to that, we would just have to in-house manufacture the individual pulleys, because they were, for whatever reason, priced much higher than the sprockets where we were looking. But that would, I think that would be a good alternative, because obviously it's also less susceptible to sand and wear. Yeah, and
it's something that probably doesn't need to carry a lot of load, so I think you'd be okay with belt instead of chain. When you had mentioned that you were looking at fatigue analysis, and you said you didn't need to do fatigue analysis of the wood because it's a brittle material.
Yeah, that's what I had estimated. Pretty much just that, as long as the maximum stress didn't go over the yield strength of the wood, that would be fine.
I think you'll find that brittle materials tend to be more sensitive to fatigue. Something that is fibrous like wood sort of alleviates that, because cracks don't tend to have paths to link up going transverse across the grain of the wood. But as a general statement, if something is more brittle, it's going to be more sensitive to fatigue. So keep that in mind. When you're doing your electronics lifetime, I'd really appreciate that you guys had maximum temperature electronics, but then if you back off by that, you tend to increase the life by some factor. I think you'd mentioned, I think it was on a previous slide to this.
Yeah,
I was going to mention this slide in just a minute. Right. So so here you're saying, you've got a maximum lifetime for 52-degree temperatures that is, you're doubling, for every 10 degrees, right? And that's how you're calculating the maximum lifetime. I really appreciate you thinking about that, because some other groups that I've seen say, oh, Arduino can operate in, 100 degrees C, and our box is under 100 degrees C, so it's good, right? And that's not all there is to it. There's certainly a maximum temperature. There is temperature cycling. Another, you mentioned the lifetime of capacitors. Another way that electronics fail is thermal cycling will break solder joints. So that's another sort of mechanism for failure. But I like that you're on the track of considering that. But I think you're claiming that your worst case temperature that the Arduino is going to be exposed to is 52 degrees Celsius. Where does that come from?
Yeah, so I was just kind of I guess to be honest, I probably should have put more thought into that number. I was just thinking about, usually the highest temperature. I guess this is what I thought in my head, but it may not have been the best option, because the maximum high temperature in Las Vegas is 47.8 degrees, but degrees Celsius, but that gave a larger year number. So I was just kind of I don't know, thinking, oh, if the 52 degrees, I was just
On
saying.
literally the very next slide, you did an analysis of the temperature inside your box, right?
Yeah, I probably, that's yeah, I guess I was just trying to like not have a huge U number there, I guess. I don't.
Well,
Yeah.
I think what he's saying is that the temperature that should have been used was the temperature from inside the box found through the heat transfer.
I guess
I think that's probably a better figure to use there. But I do like that you're considering it and you're sort of on the right track there. When you mentioned, I'll jump back to the structural analysis. You were doing structural analysis and calculating factors of safety, and it wasn't clear to me because again, Las Vegas is hot. It's it's certainly much above room temperature where material properties tend to be calculated and reported. But you also find that like temperature knockdowns, so as temperature goes up, the yield strength of a material will go down, right? Did you consider any of that in your structural analysis here?
Yes.
We did not. The extent of that we considered was that we researched at what temperature PVC begins to have changes in its material properties, which was 60 degrees Celsius. And we found that the maximum temperature in Las Vegas was only 48. And so with doing all the structural analysis, I just assumed that the temperature had no impact on the material properties themselves.
I would be pretty surprised if that were the case. I mean, it might be that they're talking about like 60 degrees Celsius, you start to have, some long-term like physical change to the atomic structure of the material or something like that. But it's, even with 60 degrees Celsius is something like 180 degrees Fahrenheit. And that, no, it's probably less than that, probably 150 degrees or so. But even at that temperature, right, like metals will have some appreciable knockdown in strength. Maybe it's 5% for aluminum at 150 to 180 degrees. I would expect PVC to see something probably bigger than metal. So I'd encourage you to take a look at that. And again, I think you've got plenty of structural capability here for that.
Yeah. I thought this would be mitigated by the fact that our yield strength was more than double or not our yield strength, our factor of safety was more than double what the customer had requested. So I thought it was an okay assumption at the time.
Yeah, like I said, I don't think it's gonna give you any problems for the structure that you've analyzed, but it is something that I'd want to see accounted for. The other thing I would sort of pick at in the structural analysis, it looks like you did structural analysis of your post and of the PVC pipes, but there's certainly more to your structure, and I wonder if any of that is potentially a weaker link than what you've analyzed here. It looks like you've analyzed kind of the big bone parts of the structure.
Yeah, we definitely did not analyze anything other than the PVC and the wood for the structure in terms of factor of safety, but I could see, now that you bring it up, potentially some failure occurring where the metal frame that holds the mirrors screws into the PVC. That might be one potential area. That is something more to look at though.
I'm not super concerned with the frame is pretty heavy duty, and where the contact points are and where the loading would be pretty close. Let me see if I can get a better view. Would be pretty close to where it's mounted to that PVC frame. But I do think we should probably, sorry, not this slide, pick a better one. I guess this is a good slide as any to show it. But certainly for not so much a concern with the failure, but more so the strain and the deformation of the structure would be something.
Why are strain and deformation important?
Because if your frame is, if you experience twisting, then obviously you're not going to point directly at the receiver. So just making sure that
I love you guys so much. Okay, so let's talk about your actual mirror support, right? I think I remember seeing that was like sort of a empty box like you know, you line the outside edge with your galvanized steel,
Mhm.
and then but it's you know, sort of got an open space in the middle, right?
Yeah, so the structure is it's basically like 450 millimeter by 60 millimeter strips of galvanized steel, and then those are overlaid in that square pattern that you can see. I don't know if you can see my cursor, but
Yeah, I can see
along the outer edge, and then there's also in between, since obviously if you overlay strips, you know, think of it kind of like Lincoln logs, you're going to have like a gap. So to flush out that gap, there's another strip that sits inside of there.
Okay.
And then
How are they attached?
They have they're welded together, spot welded.
Okay.
And then
have you ever welded galvanized steel?
So as long as you use abrasive to remove the zinc coating in the spots where
You guys are good.
the galvanization is, it should be fine.
Okay, and you've considered that in your manufacturing costs, presumably?
Yes.
Okay.